Can research that seems totally pointless actually change the world? That is the question posed by the useless knowledge principle. The idea that investigations with no obvious application can unexpectedly lead to groundbreaking discoveries. History is full of examples where scientists explored obscure or useless topics only to stumble upon revolutionary technologies. Take quantum mechanics, once considered a bizarre theory with no practical value, it now underpins everything from lasers to smartphones. Or consider number theory, once pursued purely for intellectual joy, today it powers modern cryptography. This principle suggests that curiosity-driven research, even when seemingly disconnected from real-world problems, often plants the seeds of future innovation. But why does this happen? Because nature is deeply interconnected, and exploring one question often opens unexpected doors to others. By studying something useless, researchers create new tools, frameworks, and perspectives that can be repurposed in surprising ways. Example, the discovery of X-rays came from studying cathode rays, a topic considered niche at the time. Analogy, it is like digging for fossils and accidentally hitting an oil reserve. What you find may be far more valuable than what you were looking for. The useless knowledge principle reminds us that in science, the pursuit of knowledge for its own sake is often the most powerful engine of progress. How can theoreticians design schemes to tap the immense zero-point energy of the quantum vacuum, an ever-roiling sea of virtual particles, yet find every proposal rebuffed by the bedrock rules of energy conservation? Quantum field theory depicts the vacuum not as emptiness, but as a dynamic matrix alive with fluctuations. This zero-point energy, observable in phenomena like the Casimir effect, tempts us with the prospect of a limitless power source. However, attempts to convert vacuum fluctuations into usable work invariably collide with the unyielding demands of conservation laws. So far, so good, until we examine the very foundations that make these extraction schemes conceptually possible, yet practically impossible. The quantum vacuum energy extraction paradox appears when one tries to reconcile mechanisms for harvesting vacuum energy with the principle that energy cannot be created from nothing. In an ideal isolated system where time translation symmetry holds, any net energy gain without compensatory input would violate Noether's theorem, undermining the core of both classical and quantum physics. At its core, the paradox hinges on the uncertainty principle's allowance for brief borrowing of energy, DDH. While quantum fluctuations let virtual particles wink into existence, these excursions are strictly ephemeral. Practical extraction ideas, such as using dynamic boundaries to induce photon creation in the dynamic Casimir effect, demonstrate this limitation. The observed photons always carry away exactly the work invested in moving mirrors or altering boundary conditions. The vacuum's apparent bounty is thus merely a bookkeeping transfer from the external work, not a free giveaway. Yet even the most sophisticated theoretical devices falter under closer scrutiny. Proposals invoking stochastic electrodynamics or exotic non-equilibrium processes must still account for energy dissipation and back reaction. Any boundary modulation or field variation designed to tap vacuum modes requires precise energy input. The system's Hamiltonian remains strictly bounded from below, forbidding net energy withdrawal beyond what was supplied. In practice, even microscopic leaks or imperfect control in these thought experiments collapse the scheme, restoring global energy balance. The paradox deepens when considering the nature of the vacuum's ground state. Quantum field theory defines the vacuum as the lowest energy configuration. To extract energy, one would have to push the system below its ground state, an impossibility within the theory's own framework. This is akin to pumping water uphill without expending work. Any temporary deviation must be paid back in full, ensuring no perpetual motion. At even finer scales, the interactions among quantum modes underscore the inevitability of conservation. Fluctuations in one region are compensated by shifts elsewhere. Any attempt to isolate a harvestable mode triggers counter fluctuations that negate net gain. The system's non-local correlations, encoded in the vacuum state, guarantee that energy drawn from one pocket is replenished from the surrounding field. In essence, the quantum vacuum energy extraction paradox is not a failure of imagination, but a testament to the robustness of physical law. Each fanciful extraction mechanism, from Casimir-engineered devices to mirror-driven photon factories, reveals that what looks like vacuum bounty is ultimately a reflection of the work we ourselves inject. No configuration, however clever, escapes the ledger of conservation. Much like the deep-sea submersible failure scenario, this paradox reminds us that extraordinary environments, whether the crushing depths or the quantum vacuum, expose the ultimate limits of engineering and theory alike. The vacuum may teem with energy, but its very nature ensures that the price of extraction is always paid, preserving the inviolable harmony of the universe. The useless knowledge principle highlights that research pursued without any immediate practical goal can nonetheless yield transformative breakthroughs. Historically, studies driven by pure curiosity, deemed useless at the time, have uncovered fundamental phenomena that underpin entire industries. This principle challenges the expectation that every scientific endeavor must have a clear, short-term application. It underscores the value of open-ended inquiry as a crucible for unexpected innovation. Alexander Fleming's accidental observation of mold-killing bacteria during basic research on Staphylococci led to the discovery of penicillin. It is like wandering through a dense forest without a map, only to stumble upon a hidden stream that becomes your town's lifelong water source. Applied research aims to solve specific, predefined problems, often guided by market or policy needs. In contrast, curiosity-driven research pursues questions deemed impractical and without obvious endpoints. Although applied projects tend to yield predictable outcomes, curiosity-driven work opens the door to serendipity and paradigm shifts. Recognizing the complementarity of both approaches is critical for a healthy research ecosystem. Number theory was once considered purely abstract until its principles became the backbone of modern cryptography. It is like tending a vegetable garden for immediate harvest versus exploring a wild meadow where unknown plants might reveal new medicines. At the micro level, useless studies generate data points that populate vast knowledge networks, enabling future cross-field connections. Each small insight, even if seemingly irrelevant, enriches the informational substrate from which new theories emerge. Over time, these micro-contributions coalesce into the foundations of entirely new disciplines. The emergent behavior of these networks illustrates how unanticipated links drive breakthrough innovations. Early spectroscopic studies of color perception had no application until quantum mechanics used those data to validate electron energy levels. It is like collecting seemingly random puzzle pieces that later fit together to reveal a grand picture no one initially envisioned. Serendipity arises when random or accidental findings intersect with prepared minds ready to see their significance. Recombinatorial innovation occurs as researchers recombine disparate, useless discoveries into novel applications. These mechanisms show that the true utility of knowledge often lies in its unpredictable reassembly. Thus, the path from curiosity to application is nonlinear and richly interconnected. The development of the World Wide Web stemmed from Tim Berners-Lee's need to share information at CERN, not from a commercial aim to create e-commerce. It is like mixing various colors of paint in no particular order, but later realizing the blend yields a new, striking hue ideal for a masterpiece. Serendipitous discoveries often emerge from work that had no clear practical objective, exposing blind spots in established paradigms. Laboratories that foster open-ended experiments create fertile ground for such surprises. The key is maintaining an environment where accidental observations are pursued rather than discarded. This approach transforms momentary anomalies into catalytic insights. Vulcanized rubber was discovered when Charles Goodyear accidentally dropped a mixture of rubber and sulfur onto a hot stove. It is like baking a loaf of bread and noticing a novel flavor when you stray from the recipe, then deciding to refine that variation into a new, Specialty loaf. The impact of seemingly trivial studies can snowball as each new result builds on earlier unrelated work. Nonlinear interactions among research findings amplify the long-term significance of basic science. Over decades, this cumulative effect can reshape entire technological landscapes. It demonstrates that no piece of knowledge is too small to influence future innovations. The physics of superconductivity, once purely theoretical, now underlies MRI technology and quantum computing research. It is like tiny streams converging over time to form mighty rivers that power whole cities. Funding agencies that balance support for applied projects with grants for pure curiosity-driven research maximize their nation's innovation potential. Policies favoring short-term deliverables risk starving the pipeline of foundational insights. Encouraging blue sky research acknowledges that the next big breakthrough may arise from an unexpected quarter. A diversified portfolio of research investment is therefore essential. The U.S. National Science Foundation's mandate to fund basic research has repeatedly yielded high-impact technologies decades later. It is like a diversified investment portfolio where speculative assets may outperform and stabilize overall returns. Peer review and impact metrics often undervalue research lacking immediate applications, steering scientists toward safer, applied topics. Early career researchers struggle to secure funding for projects labeled too theoretical or too preliminary. Overcoming this requires new evaluation frameworks that recognize long-term and indirect impacts. Cultivating patience and humility in research assessment is critical to preserving the pipeline of revolutionary ideas. Skilled medal-winning mathematicians frequently publish work that initially drew skepticism before finding crucial applications years later. It is like judging a chef solely on appetizers, ignoring the potential masterpiece in the main course still under development. As complexity, science, and artificial intelligence expand, useless knowledge may be algorithmically mined for hidden patterns and applications. Platforms that curate and cross-link diverse datasets will accelerate serendipitous discoveries by revealing unexpected connections. Embracing the useless knowledge principle ensures that exploration remains unshackled by narrow objectives, safeguarding the engine of long-term innovation. Ultimately, what seems useless today may become the cornerstone of tomorrow's technological revolution. Google's AI researchers discovered new materials for batteries by analyzing vast, previously underutilized chemical data sets. It is like archaeologists unearthing ancient artifacts in a forgotten site, later recognizing them as keys to understanding lost civilizations.